Good morning, everybody. My name is Martin Slabber. I'm from SARAO, or SKA, in South Africa. And we're busy building a radio telescope called the MeerKAT telescope. I'm going to tell you a bit more about how we use Ceph in this telescope. But I thought it would be interesting to look back into kind of the history of how astronomy has used data storage. It turned out to be a very, very interesting topic, and I would say like a topic for a book one day. It actually caused me to spend more time on this slide than I really should have. And hence, the first part of the slides are like nice pictures, and then the quality drops quickly because I had to do it at 2 o'clock last night. I'll give you a little bit of an overview of our Ceph clusters we have. We have multiple Ceph clusters. I'll just focus on those that's in production. Then we've done a few things special with our hardware, and I'll talk through those. And at the end, I just want to give a few screenshots of all of the tools we use. So, astronomy has always been one of those things that humans have been absolutely fascinated about. Unfortunately, we've always tended to record data. So for that, astronomy has always been like a heavy user of data recording. I still want to work out the exact bytes required for each of these observations and compare that to what we need nowadays. But a good example is of 17,000 years ago, and this is just 500 kilometers north of here in France, where they were already observing stars and logging the positions of stars by cave paintings. They got a little bit more advanced. This is an example of in California and the Chido Canyon, where you use petroglyphs, where they basically carve out astronomy symbols. It's interesting that these haven't got so much astronomical value to us right now, but astronomers are able to help date these pyroglyphs by looking at the formations that were sketched in the rock and then working back where those specific star patterns were. This was a huge advancement, I would say like the invention of SSDs nearly, where we could make our own clay tablets, and the astronomers would then punch in their little holes. This is from the Babylonian times. What's interesting thing here is the 360-day year was already established, and the 12 zodiac symbols was already recorded here. This specific tablet is about 6000 BC, but it's obviously been once much, much earlier. Here's the first example of storing astronomy data on spinning rust. It was very popular. This one is actually from close by. It's in Germany. And on that side, Sage mentioned a user interface. So I want to give him some encouragement. That is a calendar. I would not call that a very good user interface. One of the first uses of astronomy data recording that actually became very useful in modern times was from the Chinese recording data onto silk. This particular one is of comets, and for example, Halley's comet's trajectory and cycle needed such a long period of time. We needed data over such a long period of time to accurately calculate it, that this piece of silk was actually used to work out how Halley's comet actually moves. It gets a bit better, then we get into the territory of like star charts, where we record, and this is very close to kind of what the type of science that we're doing at the moment, is recording and finding new stars and recording their position over time. This is again a Chinese example where they did it on paper. We leapfrog into the AC era. Paper is still the way of recording, it's very intensive. If you read the history now, and I'm no historian, the politics starts to play here, and it becomes really interesting stories. Very famous one was the Rudolf Fine journals. These were developed by Kepler, and again, it was still paper. An interesting alternative medium then came in, and this was photographic plates. This particular one was used to prove Einstein's, this is an example of a photographic plate, but one of the first uses was to prove Einstein's theory of relativity, where they tracked Mercury passing the sun at the solar eclipse. Each one of these is very interesting. Here is I would say, a kind of an expected outcome, as punch cards became very popular. Then at some stage for VLBI, the very long baseline interferometry, people turned to very interesting and alternative ways of storing data. VHF tapes was actually used, but the tapes weren't used in a typical digital fashion as you know now, where we stored bytes. It was like literally analog data stored onto tapes. Things do go wrong. So even nowadays, when things go wrong in your cluster, just think back. I think we have got much better recovery tools than pasting this rolls of tape together. Then a jump back into paper. I think this needs no explanation, but this is the wow signal. It basically was a 7-second signal from the SETI project, the Search for Extraterrestrial Intelligence. A lot of sci-fi is based on this at the moment. And this is also something that MeerKAT is actively involved in at the moment. There is a component to MeerKAT where SETI actually will bring some equipment to us on site and continue to use our telescope to search. I'll stop the history lesson, or the just brief intro to history right there. This just brings us to where we are right now. At the moment, tape and disk. With disk, that's a whole region of SSDs as well. And then, of course, the reason we're here is the future of data storage in astronomy is definitely Ceph. It served us well. We're quite keen. We're very young team, as in like very new to Ceph. So we've still got a lot to learn. So this type of conference is very good to us. And I just want to give a shout out to the Ceph team and the developers. Thank you very much. It's helped us a lot. I'm going to give you a little bit of a talk about MeerKAT. It's very nice to be able to always speak about such an instrument and the capabilities we have. MeerKAT is situated in South Africa, so that's right at the bottom of Africa. And a section of South Africa is a semi-desert area with a very, very low population. And because of the low population, there's very little interference from humans and our activities, like telephones and computers and cars and microwaves. And so this was an ideal place for us to build a radio telescope. It's also fairly flattish, so it helps a little bit, but mostly it was the lack of humans in that area. MeerKAT consists out of 64 dishes, so each dish is an individual receiver. MeerKAT's an interferometer, so what is important is the difference, the signal difference between any two dishes, or actually at the end, between all the different dishes. Each of these dishes of MeerKAT has 4 receivers, and with a mechanical indexer, we can basically change it. So with that receiver there is what we typically call the antenna, and each one of those antennas are optimized for a specific band. There's L-band, X-band, and UHF, and S-band. Some of them, like the X-band ones, are not yet in production, but the other 3 are. Just some stats. I'm not going to talk about the stats of each dish. Those are just like little interesting snippets that people always want to know. The MeerKAT is a precursor to the square kilometer array. Many people in the science community is probably still following that. At the end, SK has different phases, but the dream is to have about 3,000 of these or slightly bigger dishes in Africa. It'll stretch out quite high up in Africa. So it's quite a challenging project. And so it was decided from a South African point of view that we are going to try and build some smaller telescopes and work our way up to this 64 dish telescope. So what we did was, I'm not going over another history lesson, but the previous one we built was KAT 7, and the KAT stands for Karoo Ray Telescope. And then we got to MeerKAT, we decided to just call it Meer of KAT 7, so more of KAT 7. Yeah, and the size, the longest baseline is at the moment 8 kilometers, so this is the furthest 2 dishes from one another. And then 70% of the dishes are all within a core of 1 kilometer. So really tightly packed in the middle, lots of dishes, and then the others are spread out. So in the previous slide, there was a number there, about 37 gigabits per second coming from each of these dishes. There's 64 of them. So it's a huge volume of data that we receive per second. Fortunately, we don't have to store all of that. What happens is, in astronomy, you throw away a lot, and then you average more. And so what we have is we've got a correlator. And this slide itself is a very interesting and fun talk. But the correlator allows us to reduce the data to a very manageable data size. At the moment, we're doing, at the peak, will be something like 24, 28 or something terabytes for an 8-hour observation. So yeah, I think it's about 3 terabytes a 3 terabytes a second or something. So it's very manageable data rates that we have at the moment. As our higher resolution systems come online, we will have some more challenging. All of the correlator processing is happening within FPGAs. We just haven't been able to find any computer that can do this type of compute. So we've built our own whole row of FPGAs. So just to give you an introduction or an idea of the data flow we use and kind of where Ceph fits in for us. So like I said, the data flows from each of these dishes into our correlator, and out of the correlator comes a scientific worthy stream of data. Before then, it's basically signals, and it needs to be correlated and filtered. What we then do is, on this side, we have our site in the Karoo, and on that side, we have the site in Cape Town. And in between is our transfer processing. Out of the correlator, it goes into the science data processing subsystem, and the science data processing does a lot of the calibration, the ingest, and some early stage imaging, and these results are stored into a Ceph cluster. We use Ceph cluster, a Ceph cluster, and with different pools to store the temporary data. So processors will read and write onto the Ceph cluster, and there we have pools that are just SSD pools, and they're basically on machines that will do the compute and the storage all mixed together. Then there's also the results of that work is also just written back to the Ceph cluster. We do then transfer this to Cape Town, where we have our large archive, which I will mention later on. And from this archive, we have the ability to publish to the world, publish to our partner organizations where they have more compute to further refine or for the scientists to specialize. We also have a small compute cluster of our own for our own internal science teams. And what comes out is the best known picture of the center of our galaxy. And that's at the moment our claim to fame for producing that. It's an enormous picture, by the way. That's just a little snippet of it. So here, all of the green lines that I put in there is our interfaces to Ceph. And from a science point of view, we do all of that with Rados Gateway. It's actually was one of our biggest moments is to realize that all of these interfaces that we need are requirements for this. We could simplify, and we could do it only with like Rados gateways. We use other things like CephFS and block devices for our other systems and for testing and just keeping things up and running. But our prime use of Ceph is basically as an S3 gateway. Here's an example of, excuse me. This is how our Karoo system works. So that was the one Ceph bubble. I've just decided to pull it out a little bit more to show how we deal with the two different pools. And for us, this was, it's very useful to be able to tell S3 to have certain buckets on SSD and certain buckets on the hard drives. And that is balances well with cost and performance, whereas we could utilize the SSDs efficiently to just do the high performance part of our workload, and the hard drives to do like the more traditional just store and wait. Our transfer daemon or transfer processes is all custom in-house software that we've developed to fulfill our needs, and that is to move our data from the site to the Karoo. And the reason we've done it ourselves is because we've got certain tokens that we look at in the data and decide when to move which observation. We also, because the site is quite far away from Cape Town and it's got kind of an unreliable fiber link, we get a few breaks a year. Our transfer daemon knows what observations to move to Cape Town first and what's needed and fills our policies that way. Our big cluster in Cape Town is fortunately very simple. It's just a big cluster using hard drives, and I'll show you some slides more. I'll put in, especially towards the end, a lot of these screenshots about our user interface because it ends up, this one in particular is, what the users see is this, and they don't really care about how many sweat and tears goes into your Ceph cluster. They just want to click and download their observations. A bit more about our team. We're quite a small team. Our whole Ceph team is here at the moment. He sits in front here. It's Thomas. And we recently had, or have Sean February join us. Myself, I'm in the infrastructure, I can't say team, infrastructure person. So every now and then I get the opportunity to play with Ceph, but most of the time I deal with the hardware and networking stuff. And also leading up, I must tell, I'm no historian or an astronomer, so if you have like really tough questions on those two, you can ask me, but I'll have to come back to you. So earlier I said I want to tell you about the hardware because that's kind of a very important part of our story, and we had to make a few very crucial decisions, and one of them that we did was we decided to develop our own storage pods. There was a lot of options on the market, and at the moment there's even better and more selection. But at that stage, when we budgeted for the MeerKAT telescope, the rand-dollar exchange was pretty nice. We would be able to buy some really nice off-the-shelf hardware. But by the time we got to procurement, what we could get for each of our rands was not a lot of dollars. So we had to like really assess what our value proposition is within our budget. And it turned out for us that if we would take your typical storage appliance and we would just carve away everything we didn't need, we ended up with a very basic piece of hardware. We tailored this piece of hardware specifically to our Ceph needs. Okay? So it's probably not the best for your general storage. I don't think this would be like your OpenStack solution of note, but for our storage requirements, it plotted out to be a very, very nice piece of hardware. Here's a photo of it. You can see our typical safety wear we have in our data center. So we teamed up with a company in Cape Town called Peralex. They specialize in building or providing solutions to the military field. So they're really good at discussing the problem with you and working through all of the solutions. One little quirk that we had at that stage was we wanted these storage pods to have a low RFI. Now, RFI is radio frequency interference, and because we've decided to go so far away from civilization to build a telescope to avoid RFI, we didn't want to now take our storage pods up into the Karoo, put them close to the telescope, and then basically cause RFI. So we have a very, very particular data center there. It's all metal cladded with like cool space-age doors. But every component you take there, you want to be really sure that it doesn't add noise. So these storage pods, besides having good airflow and performance, or specific performance for us, it also has a very low RFI footprint. Okay. I mean, you can probably read the stats, but I'm just going to give an idea. We've got 48 3.5-inch drives at the moment. We use the 8 terabyte Seagate drives. We have one NVMe in each of our boxes. We have a boot drive. We've decided to make that boot drive an SSD. We've got 128 gigs RAM, a single Xeon CPU, and our 25 gigs of network there. One of these pods might be one of your Ceph developers' worst nightmare, but like I said, it works for us. But in the process of developing this hardware, there's a lot of stumbling blocks. And one of them, fortunately for me, a lot of these stumbling blocks arrived just before I joined the storage team. I joined kind of in the same time as these boxes starting to arrive. So it's been like a Christmas ride for me all the time. One of the things that happened is as these boxes were about to go into production, the SATA controller that we chose was marked end of life. And the only means that we could get our hands on that particular card was to buy 1,000 of these cards. So that was obviously not a good option for us. So we had to basically go back to the drawing board and choose a whole set of new components. Then on the first 16 or so nodes that we received, our initial spec for these boxes was a lot less memory than I show here. And we had a Ceph cluster up and running, and it all looks good. And then at some stage, it started flapping. The OSDs just started flapping, and things went horribly wrong. And being very inexperienced with Ceph, we tried very hard to figure it out. But like the guys from Switch mentioned earlier, we phoned up the guys from CERN, and Dan helped us and quickly pointed out that the memory on these boxes were way too low. That was okay. That was fortunately easier than the RAID controller, so we could easily procure memory and up that. More recently, and I must actually state right now, a large portion of our cluster is down and waiting for us to get home. So more recently, we chose a very bad SSD because we were trying to save money and we read the forums and got the best we thought would work. But so recently we just decided to buy much better OS drives. And just before we came here, we basically went out and replaced all of the OS drives. And so we'll get a bit better, not performance, but less breakage out of our cluster. We have some other nodes that form part of our storage cluster. Now, these are our these boxes are mostly there for processing purposes, but we also let them serve as our storage nodes. So each of these boxes have 4 GPUs, 128 gigs of RAM, 2 biggish CPUs, and 21 terabyte SSDs. And those SSDs we all pull into our Ceph cluster. But these ones are, these specific boxes are all on site. We've got 24 of them, and we use them to do the astronomy processing, and then right back to the SSDs, another process picks up. This is all run on a Mesos cluster with very custom framework. Just a side note, for us, a lot of the time, we try and we have to go through the layers of abstraction to get as close to the hardware as possible to get the most performance out of our boxes. The astronomy workloads are very much like focused on you need one big box with as many CPUs and GPUs as you can throw at it to do an operation. We've since the main cluster in the Karoo is called MeerKAT, we've dubbed the one in Cape Town, which is close to the ocean, we've dubbed that SARAO. On site, we've got about, at that site, we've got about 20 petabytes. That would be the raw capacity of storage capabilities. It's comprised out of 55 of these storage boxes. That gives us nearly 3,000 OSDs at that site. So the previous speaker's talk is going to be very relevant for us. On the MeerKAT site, it's much smaller, but it's comprised out of different types of hardware. Those are the 2 storage units that I've earlier showed you earlier. Just a note on networking. We've played around with very many networking options and had a couple of suppliers bring us units to test with. And at the end, we went for the Mellanox switches. We found them to work very well. We've also opted for 25 gigabit into each of our boxes. We did not split our Ceph network from our production network for reasons to keep it just simple. We initially planned to have 2 10 gig networks, and it just worked out to be more cost effective for us to have a single 25 gigabit interface. We still have the option to do VLANing or something if we need to split those networks, but especially in the case where we have these boxes that basically provide storage and consume storage, it seemed to be just a little bit simpler to do it this way. So this is the bit of the story I feel the most kind of at home with. Because we've are such a small team, we've decided to put in as much effort as we can and automate it every step along the way. And today we're in a very good position that we can, I would say, very quickly roll out our whole processing pipeline and our whole storage cluster. We do it from bare metal up to applications gets rolled out. We use Ansible very heavily, and we use the Ceph Ansible project to roll out our Ceph. And for hardware install, we use MAS, which is a canonical product, and it's basically Metal as a Service. It's a very cool name, but it's actually super simple to use, and it allows us to install our OS on our boxes. From here on, I'm just going to show you a couple of screenshots of the tools we use. Don't worry, they are all from test clusters and stuff, so nothing here is from a production stuff. So there's also not coherent names for the people who read very fast. So this is MAS. And like I just said, MAS allows us to easily redeploy. We've had a few hiccups with MAS, and if anybody else considers using MAS for Ceph, one of the biggest gotchas for us was that MAS really wants to take control of the hardware. Basically, the hardware is under its control. And you really have to go and wrangle your hardware back if you want to do some funny things. Now with Ceph, even if you reinstall the OS, the OSD still contains all of the required metadata for you to reconstruct your node after a node failure. So our first rollout of MAS, what happened is that when you would reinstall the OS, MAS would actually go and wipe each of the OSD drives. It would do some security stuff and just clean the drives, and we couldn't recover those OSDs. So that, I mean, Ceph recovers and everything, but it kind of wastes a lot of time. So what we realized that it was very simple, that you just, before you install the OS, you have to tell MAS like not to manage each drive. That took a lot of clicking with the first few nodes to test it, but eventually we've scripted all of that. Since that, it's worked very well for us. So we use MAS basically just to get the OS on the box, and thereafter we use Ansible to do all of the other provisioning. So we don't, although MAS has capabilities to install software and launch certain processes, we don't use that. Ceph Ansible, sometimes a hate relationship, but mostly a love one. It's worked well for us. We do not deploy in a container environment. I must admit we are considering it very strongly. But at this stage, what we do is we, again, like we do with our astronomy software, we just try and get as close to the hardware and OS level deployments. Ceph Ansible supports that without any hiccups. We've had a few problems here and there, but it's mostly been resolved quite easily. One of the things that we do struggle with Ceph Ansible that I might just mention is when we restore, we've picked a version of Ceph that we want to install on all of our hardware. And if Ceph moves forward, Ceph Ansible also moves forward. And we found it difficult to install our older version. And we've developed a few workarounds around that. As a team, we always like to have insight and see what's going. In a perfect world, this is how we would like to see our full infrastructure. We would like to gather host metrics. There's a project called NetData. We're quite fond of it. It does everything we need it to do. Ceph Manager gives us a lot of metrics and information. We gather all of that into one of our favorites is Prometheus. We visualize with Grafana. We use the alert manager in Prometheus, just enough of it to kind of generate some alerts for us. There's a product called Alerter that gathers everything and give us a bit of a dashboard. I've got a slide on each of these just quickly. And then we push it out into email. There's some people who hate reading email, like myself, who want it on the IRC. And we have happy admins. But as we all know, that's not the case. Reality is kind of more like this. And we're working very hard to get back to the previous slide. But as we remove one of the links, there's just always another one popping up. Is there anything here? Yeah. So, like didn't mention before, we use Elastic Stack a lot of the time, more as like bubble gum to stick holes. We do a lot of scripting with Python. With our different hardware, there's so many ways of interfacing with them. I forgot to mention that we use Dell hardware for our mons and MGRs. So we have quite a selection of hardware. And then all of our other applications also. We've kind of unfortunately got a bit of everything there. So we've got quite a lot of different hardware platforms that we have to work with. And there the consistency is very poor. And so now I'm nearly at the end. I'm just going to race through some slides to tell you about the products we use. So this is NetData. Quite recently, I mean, a few months ago, Sean and myself found it, and we just kind of installed it onto our local nodes, and we started kind of enjoying it. We had a scientist come to us and telling us about like his applications. Its disk utilization is high, and he needs faster disks. And we were like, what? And so we installed this onto that processing node and gave him the interface. And very quickly he could like come back to us and tell us that it's something different that was the problem. So it's nice, and it also exports it as Prometheus metrics, which is very useful for us. Like so many people, we use Grafana in our environment. We only use it to store logs. Every now and then we throw in a few thousand objects, do a query and delete them, but it's quite useful in that sense. Prometheus has been very, it's been a cornerstone for us. One of the things that we had a problem with was our Cape Town storage is at the CHPC, the Center for High Performance Compute, where they have a whole HPC facility. And they were generous enough to give us a room to put our storage in. But the reason they gave us the room is because they didn't want the room, because the air conditioning in that room is a bit complicated. And I have to go to a long story to tell you which is where. But the idea is that there's no hot aisle or cold aisle. It's just one big mix of storage. And so as we packed our storage node in, it changes the airflow, and basically everything just gets very messy. So we had the need to know the exact temperature of each, not the need, I think it's more like an itch we had, that we had to scratch. And we wanted to know the exact temperature of each single drive in our whole cluster so that we could start drawing heat maps and getting ideas. So at the end, with a little bit of Python scripting and the three of us just climbing in, we were able to very quickly develop just some added labels to the Prometheus metrics that could tell us the bay number, the current SD of blocks, and so forth. And given that data, we went to the data center and we moved floor tiles around until the graphs were like, a bit spaced. I can't remember if this one was a good one or a bad one. It looks a little bit high, but we'll have to see. And this is the interface that we show to the rest of the people in our organization. And this is an example of Grafana just showing you the Ceph metrics. There's hundreds of other dashboards that you can show that has got more information, but this one has plotted out to be kind of the most useful. And I think what people care about is only two things, and that is healthy and available capacity. Tom and Sean care about the number of OSDs out. Like I've mentioned before, we use something called Alerter just to aggregate all of our alerts. There's just so many of them that you kind of just at some stage ignore too many of your emails and you never know what's important. So a little dashboard has actually become very useful. And then just like a last mention is we use something called Netbox. It's a data center information management system. So it's helped us a huge amount to keep track of all of these nodes and kind of where they all sit, and just basically physical location. What's cool about this is got an awesome API. What's cool about Mars, it's got an awesome API, and we're at the moment just baking up some Python code to kind of link the two together so that we can even do less of a clicking. It helps to be lazy. Yeah, so I just want to do a last mention that we've started a Ceph Meetup in South Africa. We so far quite a small community there. But as these things go, I mention it here because you know somebody else and somebody else knows somebody else, and maybe the word gets out there that there is a Ceph community in South Africa. We've had 2 meetups in Cape Town so far. There was two handfuls of people there, but it's all good. At the moment, it's all research related, so it's obviously our contacts that come to these things, and we're still trying to find who in industry in South Africa is using it. We're going to try and have a meetup in Johannesburg, Pretoria pretty soon. And that's it. Thank you very much.